In this video, we're going to talk about reaction mechanism, okay? So consider a hypothetical reaction. A plus B goes to C plus D, and then that's step one. And then the second step is D plus F. So D from here, the product of this first step, goes into the second step, plus another reactant, F, gives you G, okay? So now, the overall reaction, if you add these two, so this reaction contains two steps. If you add these two, you see that D cancels out here. And so the overall reaction is A plus B plus F gives you C plus G. That is the overall reaction. And what we can say is that this overall reaction is made up of these two steps. These two steps are called elementary steps. Okay, so steps 1 and 2 are elementary steps. Okay, so a reaction mechanism is essentially the series of elementary steps that make up the overall reaction. Okay, and oftentimes when we do a reaction, we explore a reaction, we see only the overall reaction. We're unable to determine what are the individual steps that make up the overall reaction. And oftentimes you have to determine that by experiment. So that's what this topic is about. The other thing that I want to mention is each of these elementary steps has a certain number of reacting species. Okay, so take a look at step 1, for example. There are two molecules that react to form C and D. So the number of molecules that react in each step is called the molecularity of the step. So we can define molecularity as number of molecules reacting in an elementary step. Okay, so in step 1, you actually have two molecules reacting. Okay, so that would be a bimolecular reaction. Okay, so bimolecular would be two reacting species. Now, if there was only one reacting species, that would be unimolecular. And if there were three reacting species, that would be termolecular. Termolecular is pretty rare. Okay, so we don't encounter this too much, but for elementary steps, unimolecular and bimolecular are more common. Now, take a look at the overall reaction out here. You cannot look at an overall reaction and say, okay, well, there are three molecules out there, so that should be termolecular. We don't talk about molecularity in overall reactions. We only talk about them in elementary steps. Another thing to notice out here, notice carefully that D that got cancelled out was a product of step 1 and a reactant of step 2. Look, the overall reaction does not have D in it. Okay, so what exactly is D? So D is called an intermediate. An intermediate is a species that is produced during the course of a reaction in one of the elementary steps and is consumed in another elementary step. Okay, so it's produced in one step and consumed in another. So at the end, you don't have any intermediate left. Okay, let's take a look at another example. This is a real reaction. There's the overall reaction. And this overall reaction is made up of two elementary steps, this one and this one. And notice carefully, you have HI as the intermediate out here, okay? And you add the two elementary steps together, that makes the overall reaction. Okay, so if you take a look at this reaction out here, there's a couple of things you can do that we cannot do with an overall reaction, okay? So number one is, for the overall reaction, there's no way for you to just look at the reaction and write out the rate law. That has to be determined by experiment. However, for elementary steps, you can write out the rate law just by looking at the equation. So the rate law for elementary step 1 can be written as rate is equal to the rate constant, let's call that K1, okay, is equal to, let's call this rate 1, is equal to the reactants raised to their coefficients, okay. So you do H2 in square brackets, that's 1, so we don't write anything out there, and then you do ICL, again that's 1, so we don't write anything. So that is the rate law for the first elementary step. The rate law for the second elementary step is R2, K2, HI raised to 1 times ICL raised to 1. Okay, so and then the overall rate law is going to be a combination of these, and then what's going to happen is in a rate law you can never ever express an intermediate. It's always going to need to have a combination of this, okay. So therefore we have to do some algebraic manipulation to be able to get rid of the HI from this expression, because HI is an intermediate, okay. So that's something we'll take a look at. Another thing to consider out here is of the two steps, these two steps occur at different rates, okay, so at different speeds, and the slow step is the one that determines the rate, okay. So we're going to write that down. The slowest step, so the step between 1 and 2, which one was the slowest step, is always the rate determining step. Now this information will be always given to you. Sometimes this is abbreviated as RDS, okay. Now if you take these two elementary steps, let's say the information that's given to you is that step 1 is the slowest step, so that's the slow step, okay. So since that's the slow step, the rate law from that step is the same as the overall rate. So the overall rate is literally rate 1 is equal to K1 times H2 times ICL. End of story, okay. Now the question that we have to answer is why is the slowest step the rate determining step? So an analogy I can think of is, imagine that there was a relay race, okay. So or let's say there's a relay race where there's two runners, let's say runner 1 and runner 2. In runner 1, and then there's two more runners out here. Runner 1 has to run this way to give the baton to runner 2, and then runner 2 continues, and the same thing happens out here. Now if runner 1 is slow, then it doesn't matter how fast runner 2 is. The speed at which runner 2 can only start running after runner 1 has reached runner 2. So the outcome of this race is going to be dictated by the slowest runner, which is runner 1. Now in the second example out here, let's say runner 2 was the slow one. So runner 1 can be super fast, but it doesn't matter, because the second runner 2 is going to get the baton. Runner 2 is going to run super slow. So the outcome of this race is going to be dictated by runner 2. And that is the analogy. When you have a sequence of steps, the slowest step is the one that dictates how fast the overall reaction takes place. Therefore, the slowest step is the rate determining step. And this is the truth for every reaction that you will come across. Let's take a look at an example where you have a fast initial step, okay. So step 1 is a fast step, and it's also reversible, by the way. So you have a forward reaction and then you have a backward reaction, okay. And out here you can see there's a K1 for the forward and a K-1 for the backward. So each of these reactions has a rate, and the rate for the forward has a rate constant of K1, the rate for the backward or reverse has a rate constant of K-1. Okay, and then you have a second step, which is the slow step, and then the final step is the fast step, and the overall is given to you out here, and we cancel out the intermediates. Okay, so as we said previously, the slowest step is what determines the rate. So let's go ahead and write the rate law for the slowest step. Okay, so the rate for this step, let's call that rate 2, is equal to k, let's call the rate constant for this is k2, times h2 times N2O2. Okay, and there's only one of them, so therefore we have 1 as the exponent in each case. Now we could go with this. The only challenge is that N2O2 is an intermediate, so it doesn't show up as any of the reactants in the overall reaction. Therefore, we have to kind of find a way to replace the N2O2. That's where we use the first step and do some algebraic manipulation. So for the first step, let's go ahead and write what we get for the first step. I'm going to write that down here. So for the forward reaction, the rate of the forward reaction, let's call that rate 1 since we have that out there. Rate 1 is equal to K1 times NO raised to 2. And then the rate of the reverse reaction, okay, call that rate -1, is equal to K -1 times, because we're going this way, so therefore that's the reactant in the reverse case is going to be N2O2. Okay, now since that reaction is reversible, the forward reaction is the same as it occurs at the same rate as the reverse reaction. Therefore, these two rates are equal to each other. Therefore, we can take this and equate that to that. Okay, so therefore we can write K1 times NO square is equal to K minus 1 times N2O2. Now, we're looking to replace this, okay? So we'll just go ahead and isolate that term out here. So we get N2O2 is equal to K1 over K minus 1 times NO square. Now let's go ahead and take that and plug it in here. So that's going to give me K2 times H2 times K1 over K -1 times NO square. Let's go ahead and combine all the K's. So we write K2 times K1 over K minus 1. Then we write H2. Then we write NO square. Now notice carefully, we have terms out here that are actual reactants in the overall reaction. Okay, so that's good. Okay, and then we'll replace that with just a regular K, because that a combination of constants is still a constant. So that's the overall rate constant times H2 times NO square, and that is the rate law for the overall reaction.